the top. Welcome back. I am tasked with reminding you that if you have finished trivia, please bring up your trivia sheets to our trivia czar up here. Thank you very much. And then we will begin the night with our first fabulous talk.
I don't know how.
Let's keep that enthusiasm.
The people are excited. Let me introduce our fabulous first speaker in astronomy undergrad at the University of Washington. He's asked that I introduce him by his full name. Please give a warm welcome to Keyan Robert Leroy Gootkin.
Can everyone hear me? Yeah? Feeling good? All right. How you guys doing tonight? Fantastic. Thanks for coming out on this slightly chilly day to learn about how silly and frivolous I am. So, for those of you that don't know, the name of this talk that I'm giving is based on the Untitled Goose game, 2019 release on the Switch. Basically, for those who don't know, you play as a goose that wreaks havoc, which felt appropriate to the chaos that's about to ensue. So, without any further ado, who am I? My name is Keyan, Robert Leroy Gootkin. I'm an undergraduate at UW. Yeah, don't tell my mom. Actually, my mom's probably watching right now. Hi, Mom and Grandma, maybe. Whoop. Ooh, spoilers. Yeah, I study massive stars, although I'm not going to talk about that much. Because really, I'm here as a paragon of academic integrity. This is going to be a very serious talk, and you should treat it as such. I make normal decisions, so you're going to feel, these are going to be relatable decisions. And here's me. This is a screen cap of the game. So let's get going. So yeah, we want to talk about what is academic integrity. And as you might have seen, it's not this. Because if you look at Hasbro's website, all players draw 7 letters, and if we look back, 1, 2, 3, 4, 5, 6, 7, 8, 9 letters, perfect example. You can go to this website, although it didn't actually have the picture on there, I just needed to cite it to keep up with my theme. So we're gonna go, this is what UW considers to be academic misconduct, which is, academic misconduct. So can, everyone who's ever done one of these, can you raise your hand? Maybe in high school or college? I'm seeing some hands. All right, yeah, Thomas. Raise your hand, Thomas. Well, I fooled you. I'm a cop. I brought in, this is Frank. He's going to take you all to jail now. Yeah, so we got plagiarism, cheating, falsification, a lot of standard stuff. One way that you don't get Frank to take you to jail is you want to do some citations. Honk, says the goose. If I don't say says the goose, you might think that honk are my words. And we wouldn't want that. I wouldn't want to take credit for those beautiful words. So, we've got some examples. So it gives credit for example, the force of gravity is proportional to mass. Newton really came up with that idea, so we want to give him credit. You can also, give some more weight behind your arguments if you're citing someone who's an expert, such as "You must go fast," quote Sonic 2020. Or make sure that you don't have to explain anything. For example, if I'm talking about special relativity, that's complicated, and if that's not the topic of my paper, I don't really want to go into it too much. So we're gonna just cite Einstein and say, go read his stuff. He explains it better. These are all equal citations in the eyes of the law, in the eyes of Frank. So you cite, when you're looking for citations, really you're just reading a lot. and you just read paper after paper after paper. You do a lot of keyword searches, and eventually you find something that you want to put into your paper. So you add one sentence, and then you repeat until you have just so many. It can take a long time. It can, yeah. Oh, it went in slow-mo. That's fun. Yeah, it sort of feels like that sometimes. It can sometimes be a bit of a slog. It can be kind of tedious. But, I don't think it has to be. Academic integrity is important, and it should feel important when you're doing it. It shouldn't just be something that you feel forced to do. Here's some examples of really interesting things you can find in papers. This is a math paper, and you see here they quote T.J. Kaczynski. He's better known for other work. If you don't know who T.J. Kaczynski is, he is the Unabomber. And so, you do have the paper had to cite him, because otherwise they'd be stealing his work. But I think they worked it in well. He was better known for other work. And here's something exciting that my research advisor, Emily Lebeck, told me about today. This is a paper by, and that's not a lie, his name is Norbert. And I just thought that was fun. But this is a paper from 1987, and they're talking about the observations they had taken. And I just want to take you through this really quick step by step. No data were taken at Station D during the period 8:30 to 4:30. And what's the reason? It was due to the presence of a red racer snake. That's the scientific name, draped across the high-tension wires. And you might want to close your ears right now if you don't want to hear about animals just getting zapped with 33,000 volts that was serving the station. But critically, even though the snake, or rather a 3-foot section of its remains, was caught in the act of causing an arc between the transmission lines, we do not consider it responsible for the loss of data. No. Rather, we blame the incompetence, and I think this is me. That's just too much, Norbert. The incompetence of a red-tailed hawk who had apparently built a defective nest that fell off the top of the nearby transmission tower, casting her nestlings to the ground, along with their entire food reserve, consisting of, and they didn't have to include this, they could have stopped here, but they did list the different varieties of rat, the pack rat, a kangaroo rat, several snakes, with the exception of the above-mentioned snake, who had a somewhat higher density, and they do feel it's necessary to say, no comparable loss of data occurred at other entities. This was a one-off, believe it or not. This is the type of complete honesty and utter integrity you want in any paper that you are writing. So, yeah, science can be fun, right? That's fun. I think that's fun. I make normal decisions. But let's talk about what I have done, because I want to enter the realm of ridiculous citations, dumb stories, normal decision making. So I study massive stars. One of those stars is P Cygni in the constellation Cygnus. And so part of the paper writing process, I'm writing an introduction, and I want to introduce the readers to what P Cygni is. You don't need to know. It's too much for this, because what I really wanted to do is I wanted to find the first recording of it being discovered, because actually, unlike a lot of stars, P Cygni was too dim to be seen before 1600. But then suddenly in 1600, it got really bright and was discovered for the very first time. Even before, this is about the time that telescopes were being invented, but people weren't using telescopes looking for stars. And I actually was inspired by this YouTube video by UW's own James Davenport for the love of old books and older science. Is James here? Is Jim Davenport here tonight? He gives talks here, but he talks about how there can be a little bit of a game that academics like to play where you try and get just the oldest citation that you can, because it feels cool to be able to back up what you're saying with say, yeah, well, this is also what Ptolemy said, and 3,000 years ago. It makes you feel good when you're trying to just stave off the imposter syndrome. So it turns out actually that P Cygni was the first recording of it being discovered was on a globe by Willem Janszoon Blauw. I call him Willie. And so he made this globe. He was a student of Tycho Brahe, who's a famous astronomer, and he was Europe's best globe maker in the 1600s, for whatever that's worth. But he made this globe of the sky, and there's legends that on one of those globes he wrote an inscription talking about how he found a new star in the constellation Cygnus. But none of the papers that talk about that globe ever cite any sources. So I'm sitting here, I'm thinking, I want to know more about this globe. And can I trust these authors? They obviously aren't living up to my high expectations of academic integrity, and I will send Frank to take them to jail. And so I wanted to find out more. And so the hunt begins. And so what they said is that most of the papers said it was in a Prague museum, which isn't helpful considering that there are 80 museums in Prague. I also appreciate that I can just Google how many museums are in Prague and I can get the answer. It turns out none of these museums are of globes. I checked really hard. I spent maybe a week, 2 weeks, just this gnawing at the back of my mind. I was looking up, I need to figure out who I can call at these museums to ask about this obscure 16th century globe. It turns out UW has a Czech department. I was getting ready to ask some Czech professor if they knew anything about a globe in a Prague museum, air quotes. But eventually, and this was weeks of work. Actually, Keyan, raise your hand, finally cracked the code. And it turned out that it was actually this place. This is a castle in Sweden called Skokloster Castle. It's about an hour train ride north of Stockholm. And so they claim to have this globe here. So I thought, okay, I found it. I could put that in my paper. But then I thought, is it really there? How do I know? How do I know that it's there? So I met my best friend in the whole world, Inger. I emailed them and basically said, hi, I'm a very professional and very serious astronomer. Can you tell me where this globe is? And I got to do the very fun activity of coming to group meeting. Everyone that works on massive stars, we all get together and say, oh, I made this plot, found out this new thing, gave this talk. And I got to say, oh, by the way, the castle emailed me back. And Inger told me, this is just the beginning. Thank you so much for your question about the globe and the collections of Skokloster Castle. It's always interesting for us when objects in our collection is in focus. And that just warmed my heart. Inger, just the kindest, most helpful person I've ever emailed. She sent me a picture, actually, of the globe, and confirmed that it was there, that the inscription talked about P Cygni. Actually, Thomas helped me to...
Yeah, Thomas!
Helped me to translate the pseudo-Latin that it was written in. It seemed like Blauw didn't know Latin that well. It was kind of mixed with Dutch. But, talked about that. Figured out that it was there, and so... Mission accomplished. We have a citation. We got a citation. It's going to go in the paper. I talked to Paul Scody, who's told me that I could put a globe as a citation. That was good enough. So, short talk, I guess. But I don't know. There's still some doubt. I mean, we love Inger. We would never send Frank after Inger. But how do I really know that it's there? It's almost like, I don't know, like there's really only one way to do it. I thought to myself, gosh darn, gonna have to do a globe trip. And so, started doing some research. This is where Skokloster is. This is Stockholm, the capital of Sweden. Got Denmark, so you can imagine over here on the tarp is Russia coming around. And it's about 4,000 to 5,000 miles, and I thought, yeah, sure, why not? Anything to keep my title as a paragon of academic integrity intact. Any cost. And so I went to Sweden. I bought a plane ticket. I traveled hours, did the terrible, terrible task of getting a lay of the land, seeing all the beautiful sights of Stockholm. It was really terrible. Then I went to, it's a beautiful country. It's ridiculous. Took a train north, and eventually I had to transfer to a bus, and I almost didn't make it. The bus that I had to take to the castle, it was on a different system than the transit card that I had, and the only person in the whole bus depot, this big open parking lot, was this just very old Swedish lady, and I didn't know what was happening. I walked up to her, and I asked in my very bad Swedish, talar du engelska, which is, do you speak English? And she said, no. Luckily, I did have I hired a police sketch artist to do this portrait of her, so I would never forget her face. But eventually I figured it out, just with the help of this lady. We both laughed at me. She laughed at me first. But it was in jest, I guess. But I figured it out. I found the bus. I got there after, hours and hours and hours of travel. I finally got here. This is a picture I took with my own camera. This is the castle. It was beautiful, out in the middle of just nowhere, right next to this lake, this ancient castle in pastoral Sweden. And I found it. I found the globe. Here it is. There we are. Never doubt my integrity. And there it was. I found it. I stood there probably for an hour and just sort of stood there like I was a guide, like maybe some of a bunch of German tourists were gonna ask me questions about the globe maybe. I'm like, yeah, I know everything about this. Here's this inscription. This is what it says. It turns out they didn't think it was as cool as I did, but I had a great time. And I confirmed that it was there. And here's the inscription. Beautiful. I actually now have this as a tattoo, just because I'm a ridiculous man who makes frivolous and silly decisions. And here it is. The final product. The subject of this paper, P. Cygni, was discovered on August 18, 1600. The Dutch cartographer, globe maker, and former student of Tycho Brahe, Willem Janszoon Willy, observed the Nova Stella in the heart of Cygnus. Wow, 1602. Bing bang, there it is. I spent all those hours, way too much money, and just spent... This was really like 3 months of my life. He chronicled his discovery on an inscription on the celestial globe, which he made in his Amsterdam workshop in 1602. And I did include the footnote just because these 2 sentences weren't enough for me. I needed a third. The globe, as of the writing of this paper, because you never know. I don't want anyone to call me a liar. It's in the collections of Skokloster Castle and Museum north of Stockholm. And I even included a link so that for posterity, people would know. People would always know. But wait, that's not Skokloster. I got this message from my research advisor, Emily Lebec, not but 2 weeks ago. She was in Rome, and she went into a library, and she said, wait, that globe looks familiar. And in fact, this is Willy Blau from 1 year after. So I did find the original, but there's more out there. The story is still being written. Maybe there is somewhere in Prague, in quote, a Prague museum, a third. There might be a fourth, who knows? This was, of course, Europe's most prolific globe maker. Guess we'll have to find out some other time. I'll have to come back once I go to Rome, travel around the world. This is my life's work now, I think. It certainly feels like it, but thank you so much. Does anyone have any questions? Does anyone have any questions? Yeah, right here.
Okay, so how do you know if your globe was the original one?
Fantastic. The question was, how do you know that my globe was the original? I choose to believe. So we know that the one in Rome, it did say that globe was made in 1603. If you remember, mine was, we got it right here, 1602. So we're good. We're good on that one at least. If there's other globes, I don't know. I choose to believe that it is so. I choose to believe I didn't waste 3 months of my life, thousands. So I do resent that question. Thank you. Thank you. Any other questions? Nicole.
The citation says 1602, but you say that it was discovered in 1600. Why is there a 2-year gap there?
Yeah, so the question is why, if it was discovered and it became visible in 1600, August 18th of 1600, why is my citation from 1602, couldn't I trim it down a couple years? Again, I choose. Really, I guess there weren't that many people writing about stars. That the next closest reference to it is in 1603, the Bayer astronomical, I forget what it's called. There's just a bunch of maps of different constellations in the sky, and that's from 1603. There aren't a lot of writings about it that have survived, but everywhere in the literature, they were talking about this globe, and even though they didn't cite it, and they are going to go to jail, but I think, and it does, Blau was a master of his work. I think he just took a long time to actually get this thing out. It's really beautiful, like there in person, like the picture here, you can imagine it looks really big, but, and actually the castle, the website, the globe, the picture of the globe that they have there, they have it photoshopped for some reason, so that it looks like it's the size of a room, and I was really confused by that, so I got there and I was like, wasn't sure, like, am I gonna have to like, are they gonna have to wheel it out or anything like that just for me? But no, it's really small and just beautiful and intricate, and I believe that he did all of the illustrations himself, so I think it just took a long time. I feel like he wouldn't have bragged as hard as he did in the inscription if other people were talking about it. Because he goes on, he's like, on this day I did discover in the heart of sickness, look at me. These are longitude and latitude lines. He's like, look, I was right here. Which I think is a really cool flex on everyone else at the time. Yeah. Do you have any other questions? Anyone else want to just ruin my self-esteem? Yeah. That's a great question. What were they used for is the question. So this globe was actually part of a set, and it was apparently in vogue at the time for globe makers to make a globe of the Earth, where it would be like actual cartography, and then have the globe of the Earth be made with a pair of the sky. And I think this one of the sky was more just for fashion than anything. People were definitely actually using the globes of the like Europe and Africa to like plot journeys and whatnot. But as Europe's premier globe maker, you're making globes for royalty, dukes and duchesses and whatnot. I think that this one in particular was more, it was more about the clout than anything. Yeah. Yeah, John?
Were you able to meet Ingo?
Inger?
Yeah.
No! This is one of the greatest regrets of my life. I did not meet my best friend Inger. I sent her an email, a follow-up email. I was like, by the way, I am, crazy thing. Turns out I'm gonna be in Sweden this summer. I tried to play it really cool. I didn't want to embarrass myself in front of Inger. But it turns out that the Swedes all get 6 weeks or something like that of paid vacation, and so she was off having a vacation. Those slackers. But I did get a couple more very nice, very sweet emails from Inger. They went directly into the folder in my email titled Happy Emails. Just if I need a smile, just take a peek. Maybe one more question if anyone has one? Yes, way back there.
Just in the interest of thoroughness, since this presentation is all about being thorough.
I'm very thorough.
What steps, if any, do you take to actually authenticate the provenance of the globe?
I'll go. So yeah, the question was, what steps did I take to authenticate this globe?
And how do you know it was manufactured in Amsterdam? I saw that in your body there.
That was from Inger, a trusted source. You will not denigrate Inger in this venue. Frank! I did go and I did check. At first I was actually worried because Cygnus, this part of the globe, for some reason that I will never understand, was turned to the wall. So I was worried. I'm like, I don't see my boy. I don't see where. I did maybe. Don't tell Inger I did this. I did maybe scoot behind the table to be able to get a look and read the inscription myself. Frank's gone. Okay. Too many people to arrest this night anyway. Is that good enough for you? Okay, shrug your emoticon. Thank you, everyone, for listening. Letting me embarrass myself like that. I love it.
One more round of applause for Keyan.
All right, welcome back from that rip-roaring adventure, chasing a globe. And congratulations again to our trivia winners. Please give a very warm welcome to astrobiology graduate student at the University of Washington, Diana Windemuth.
Hi everyone. Okay, can everyone hear me okay? Alright, I'll try to speak loud. Okay, so I'm gonna give you, my name is Diana. I'm gonna give you a prelude of things to come that is really exciting for the exoplanets community. And this future space mission concepts that I'll be talking about has been designed with the utmost integrity, Keyan, with the question of understanding our place in the universe in mind. Okay. So these are, let me see if I can figure this out. Okay. This is a landscape of our kind of current, upcoming, and future space mission concepts. This is for NASA only. The Europeans have their own missions, but I won't be talking about them. And in particular, LUVOIR and HABEX will be directly imaging planets themselves, while OST, the Origin Space Telescope, will be observing the thermal emission from planets and the what's called transit transmission spectroscopy, which I'll talk a little bit about later. So here are our players. Oh, that's LUVOIR. I'm going to be mostly focusing on LUVOIR, which is illustrated down here. Okay, so like I was saying, these space missions have been designed to answer two fundamental questions. One, are we alone? And two, are we weird? So these two questions really encompass things like, are we alone? How do we detect the conditions for habitability, and how do we detect signatures of life? Are we weird? What is the diversity of exoplanets and planetary systems out there? And so to answer these two questions, we really need a space mission that can give us statistical studies of many groups of exoplanets, and also deep, comprehensive studies of individual planets themselves. Okay, so before I talk about the future, I have to talk about the present. So I'll give you some highlights of the field so far. So this is a figure that shows kind of the discovery/detection space of exoplanets. So on the bottom here is orbital separation. That's the distance that the planet is from the star. And on this axis here, it's the planet mass in terms of Earth masses. and over here it's the planet's radius in terms of Earth radii. So notice that these are log scales, and these different symbols here show you how they were discovered or the method of detection. So as you can see, there are huge swaths of space here carved out by these different detection techniques. Direct imaging, which is actually looking at taking a picture of the planet themselves, is in this space up here, so very massive planets, very bright planets, out at very large distances to the stars. The transit method, which many of you probably have heard of with Kepler and TESS, is carving out this space here that's very close into the host stars of these planets, and that's because it's easier to detect transits when the planets are closer, and the probability of transiting is higher when the planets are closer. And also there are some radial velocity detections, which also favors closer in planets. So conspicuously missing in this discovery space, detection space, is look over here. We've got Earth, Venus, Uranus, Neptune, Saturn, Jupiter. This space that defines our solar system, we have no currently means of really detecting. So this is an issue. Okay, so whereas Kepler and the transit method, it was really good for telling us something about the statistics, the demographics of exoplanets. And so one question that we're all interested in is how common are Earth-like planets? So this is the news story that we get every month or so where we see a new Earth-like planet has been discovered. So so when we say Earth-like, we mean that this planet has radii that's relatively the same size as Earth. It could be a factor of 2 difference, it could be a 20% difference, depending on how people define it. Orbiting a star like the Sun in the same region of space as Earth. So it does not mean that, the planet is actually hosting life. So Kepler, one of the kind of crowning achievements of Kepler was that it was able to start to answer this question. So in the next plots, you'll see some symbols. This symbol here means the planet occurrence rate density, and it's just a fancy way of saying how many planets are there per range of periods or orbital distances per range of planet size. And once you have that, by looking at the data, at the transit data, then you can calculate the frequency of Earth-like planets around Sun-like stars by specifying some radius or size bin and period bin. Okay. This is a conglomeration of results spanning nearly a decade of work. You'll see on the bottom here, this is a log space. So that means that this planet occurrence rate density is spanning from point 0 to 01 to 10. I can do math. This is a huge range, and at first I was like, doesn't seem good. But I think the way to interpret this is not that people haven't been working hard on it. The way to interpret this is that there is a lot of uncertainty in this specific parameter space because the data that we have just isn't constraining enough. We have to extrapolate from short period data to knowledge or predictions about what planets are like further out. Okay. So a group of experts in exoplanets, they got together with some community input, and they're like, well, we can't, this doesn't look good. So they got together and they investigated what was behind these discrepancies. Again, it's really a reflection of the uncertainty because the data isn't good enough yet. And they came up with ways to standardize the calculation so that moving forward we could have a better means of predicting things. And so what they ended up saying was, let's see, this eta Earth here, which is the frequency of Earth-like planets, meaning planets with size about 0.8 to 1.4 size of the Earth in a radius, in a orbital separation that would make it be in the habitable zone, so conditions so that the temperature is warm enough that it can sustain surface liquid water. And they came up with this number here. And you'll see that there's a large range, and that range, again, reflects the uncertainty. So this number is important because it has significant implications on what we can observe in future direct imaging missions. Okay, so going back to this plot, now let's look at where we are in terms of direct imaging. So this is not looking at light from the stars and seeing blips of light, like in transit, but looking at the planets themselves. So this is the current state of the art with HST. This is direct imaging of the planet around Fomalhaut. So the star in the center here is suppressed with a coronagraph, and there's a ring of debris, dust material, and you'll see there's a planet here, and it's going to move in a moment. Aha! Really high-tech stuff. No, it really is. And, but what you'll notice is the scale here. This is 20 AU, so that's kind of between the orbit of Uranus and Neptune. So this is probing at very large distances from that central star. So very different from our own solar system. Let's skip this one. Okay. So in terms of characterizing the actual planets themselves, we're limited to this technique called transit transmission spectroscopy. And the way that we, this is one way that we can probe the atmospheres of exoplanets. One thing to note is that transit transmission spectroscopy means that a planet has to transit or pass directly in front of a star in order for us to probe the atmosphere of that planet. So perhaps many of you are familiar with the transit method. What happens in transit transmission spectroscopy is, here's a cartoon of it. Here's some planet with a really large atmosphere. Maybe this is gas giant. And you have some starlight, and we're observing over there somewhere. And so what happens is, if you look at a white light curve, a white light, then you'll see that, you know, the star will be bright, 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 and then it'll go dark, a little dim as the planet goes in front of it, and then it'll go back to the original brightness of the star. In transit transmission spectroscopy, we're looking at different wavelengths of light and looking at how the brightness of the star is changing as a function of wavelength. And going back to this cartoon, essentially what's happening, right, is you have some photons from the star. It's going through the atmosphere. Remember, we're observing over here. And some photons will make it through the atmosphere toward us. Some photons will be scattered away. so we don't see them or detect them. And some photons will be absorbed by whatever molecule is in that atmosphere. And when that photon is absorbed, right, we won't, it makes the brightness darker because we're missing photons. And so that translates to this, these different sets of transit light curves here, where for different wavelengths of light, the transit depths are actually different because the planet will appear more opaque just at certain wavelengths that the molecules are absorbing, and so the transits are deeper than at other wavelengths. So if you kind of rotate this the other way around, you'll see as a function of wavelength, the planet size or the transit depth, and you'll see that it varies. And these two blips here, so the further up it is, the deeper the transit, meaning the more photons are being absorbed. So these two are absorption features of sodium. So this is a long-winded way of explaining how transmission spectroscopy works. This is really great, but we have limited targets. And this technique really is only great currently for really large gas giants orbiting around M dwarfs because of, again, that transit geometry constraint. So we have to see planets that are close in. We need bright stars in order to get enough photons to detect these things. So that means the stars have to be really close to us or intrinsically bright. And statistically speaking, M dwarfs, which are the lowest mass stars, are most common in the universe, so they will be closer to us. And we need large transit depths to get signals. And so that means larger planet radii or smaller size stars. So again, M dwarfs. So the takeaway is that, again, our current technologies, we're probing the atmospheres of hot Jupiters, maybe Neptune or sub-Neptune sized planets around mostly M dwarfs. Planets that are not like us. Okay, so why are future space missions interested in direct imaging? Well, the pros are that we can survey entire planetary systems because you're literally taking a snapshot of the planets, maybe asteroid belt, debris, stuff around it. And we're surveying these planetary systems that are most similar to our own because direct imaging is sensitive to planets that are further out than other techniques. And arguably, we know the sun the best out of all the stars out there. So we understand stars like the sun the best, which is good in terms of how we can interpret our planet results. With direct imaging, we're directly imaging the reflected light from planets, and with that we can better probe the atmospheres of those planets, and we can even probe some surface features. We can't do this with transmission spectroscopy. And you can observe the planet at different phases. And this is important because if we detect a certain molecule of interest, say oxygen, on some planet, we can't say with certainty, right, that there's life out there. So in order to confirm these biosignatures, we need to study the planets with as much observational information as possible. So looking at the planet at different phases is one way to discriminate false positives or imposters. And again, there's no fortuitous alignment required as with transits, so we'll just get more targets out there. If you imagine planetary systems are just randomly distributed on the sky at different inclinations, statistics tells us that we'll get more targets. However, the cons are that we can't get direct measurements of the size or mass of the planets. And also, it is extremely difficult because we're imaging, when we look at the planet, the star is also in the way. We need a contrast of 10 to the minus 10. That's a lot. So to give you a scale of, the scale of things, 10 to the minus 10 contrast is like trying to image a firefly that's 6 feet away from some like super bright searchlight. That's great. I can see the firefly right here. What are you talking about? Well, remember that planets stars are far away. So you're trying to see this firelight against the glare of this searchlight from a distance like from Seattle to Boston. So that's a really, really high contrast and high resolution problem. So the answer is go to space. Now, and the answer is use coronagraphs. So how does a coronagraph work, and how does it help us detect the faint planets next to the really bright stars? So I'm going to be playing this NASA video and attempt to narrate over it. Okay. So we're searching for life, habitable worlds, and we want to detect these really, really faint planets against the glare of stars. Space, the final frontier. Okay, I'm really excited about the card. Okay, so we have some distant planets, an Earth and a Jupiter analog that's orbiting a star, perhaps a nearby star in the solar neighborhood. And now we're pointing our telescope at it. The light from the star travels through space, enters the telescope, and is detected as a central source, an airy disk, with concentric rings due to diffraction. To reveal the planets, we use this coronagraph mask to block out the central source, and then we use a lyode stop to suppress the light from that diffraction pattern. The planet, because it's physically offset from the star, the planet's light will come in at an angle, and so it misses the mask, and the photons make it to the detector. However, because in reality there are imperfections with the telescope mirror and the optics system, those imperfections will cause wavefront errors, which will imprint as this speckle here in the image. To remove this speckle, the telescope uses deformable mirrors to correct those wavefront errors in real time. And so eventually you can see the planets out here. And if there are enough photons coming from the planets, we can pass their light through a prism to look at their spectral components. So here some light is missing, and those light are being absorbed away by different molecules in the atmospheres of those planets. So that's how, that's called direct spectroscopy, and that's how we can use them to characterize atmospheres of exoplanets like Earth that's far away. Okay, so going back to the future space missions, LUVOIR and HABEX, like I said in the beginning, are focusing on this direct imaging problem. So they will fly with coronagraphs, and the main difference in LUVOIR and HABEX is they have very similar science goals, right? To detect biosignatures on exo-Earths. But their ambitions are very different. And so I will mostly be talking about LUVOIR tonight because I think it really tries to go boldly in its ambitions of actually surveying many exoplanets in order to say something statistically meaningful about these exo-Earths. so we can actually place constraints on the frequency of habitable conditions and detect potentially life on other planets. Okay, so what is LUVOIR? It's not French. It stands for the Large UV Optical IR Surveyor. So these are the wavelengths of light that it will be looking at. Remember, these are space, perhaps I didn't highlight it in the beginning, but this is a space mission concept, meaning that it hasn't been decided that it will fly yet. It'll be decided by a panel of experts which of these missions will go. And the LUVOIR team designed two different concepts with one single architecture. LUVOIR is designed to be serviceable, just like Hubble. And the two different concepts are LUVOIR A and B, with the main difference being that LUVOIR A is huge and LUVOIR B is big. So to give you a scale of size, here's the Hubble Space Telescope, our favorite for now. And this is the size of their of the aperture, the mirror. So this is JWST, which will launch soon. LUVOIR B's aperture size and LUVOIR A's aperture size. It's 15 meters. It's huge. So this is a video, a simulation of how LUVOIR would deploy. So this is after it makes it to the L2 position, which is further away than where Hubble is now. So you see that the solar panels are coming out. This is how the telescope will get energy. Here comes the sunshade. This shields the instruments from radiation from the sun and from Earth and other stuff. Now the secondary mirror is coming into position, and the primary mirror, which is segmented, will unfold itself in space. And that's that. All right. So LUVOIR has really powerful capabilities because of its really large aperture mirror in conjunction with the coronagraph that will be on it. Why astronomers love large apertures is because a larger aperture provides higher light collecting power, so we're bigger so we can collect more photons, and higher resolving power. Because we're bigger, we can tell two things apart further away better. So to illustrate the resolution power of LUVOIR, here's our favorite dwarf planet Pluto. And this is with HST. This is a simulation with JWST. Here's LUVOIR B, and here's what it would look like with LUVOIR A. Really, really high resolution. And another thing that's important for our interest in detecting exo-Earths is that a large aperture gives us a smaller, what's called an inner working angle. So this inner working angle is the smallest angle on the night sky, inside where you get really bad contrast, you get stray light, but outside that inner working angle, you achieve that 10 to the minus 10 high contrast, imaging contrast. So why does this matter, this small inner working angle? Well, let's use a toy model. We have the sun and the Earth, a pale blue dot. Wow, you can't see the sun at all in this projector. Okay, believe me, there's a sun here. Oh, now I remember why you can't see it. The inner working angle. The coronagraph is working. There's a coronagraph here. right? And there's an inner working angle of some degree. And it's blocking out the starlight. Great. We're observing this system. Okay, and now let's say, wow, I really should have put a line here to denote where the star is. So this is the star here, this is the star here. But as we look out at systems that are, if we place this system further and further away, right, the planet will appear closer and closer to its star on the sky. You're with me? Okay. Until, I did not think this through. Until the planet down here, invisible, because it's within the inner working angle, everything is working as it's supposed to. All right, so another way of thinking about this is that, right, instead of this being going from systems that are more and more distant from us, we can think of it as this is a star that's like the sun, this is a star that's a little bit less massive than the sun, and this is a system where the star is an M-dwarf. And the reason why is because we want to image exo-Earths, and so an exo-Earth will be closer to the M-dwarf in order for it to be habitable than it would be for a star like the sun. And so if you're imaging, if you're looking for exo-Earths around M-dwarfs, that inner working angle will really prevent you from detecting them because they're within this inner working angle. So we'll do some high-level math here. So the smaller your inner working angle, the larger volume in 3D space you'll sample because you're looking at more distant, you're able to see more and more distant systems, right? And you get more stellar targets. And so that gives you a higher exo-Earth yield. So this is with our toy model. But with more sophisticated models, we can see what the predicted exo-Earth yield is for LUVOIR for both the A concept, the 15-meter, and the 8-meter concept. So instead of the toy model back here, here's an actual simulated observation of the inner solar system at 12 parsecs away, and with real noise properties. So this is what it might look like. And here is a figure showing the exo-Earth yield along, so it's 54-ish, 50-ish for LUVOIR A and 30-ish for LUVOIR B. This is great news because it means that we can observe potentially many exo-Earths and potentially detect biosignatures on them. You also get a lot, because you're imaging, right, because you're taking a picture of these planetary systems, you're getting, while you're searching for these exo-Earths, all different types of planets that might be in that system. And so you can get rocky planets that are not within that habitable Goldilocks zone. You'll get super-Earths, sub-Neptunes, Neptunes, Jupiters, all sorts of things. So this is great for a burgeoning field of comparative exoplanetology. Okay, so I'm gonna see what the time is. Okay, so I'm gonna skip these because unfortunately time is limited. Okay, biosignatures, detecting life or signs of life on other planets. So again, we can't send probes or rovers or landers or orbiters to planets outside of our solar system. So we can only rely on the photons that we have and remote sensing techniques. These remote sensing techniques, by looking at the reflected light of the planets, we can use these techniques to identify biosignatures. So these are signs of life in the atmospheres or perhaps the surface of that exoplanet. So in particular, you can look for specific combinations of gases. For example, oxygen and methane together is believed to be a robust detection for the potential of life. And underscore this combination of gases here because we don't want to just look for one molecular absorption signal, because there are many false positives, meaning there are many non-biological processes that can produce different molecules in the atmosphere, right? It's only when you look at combinations of gases or molecules and kind of disentangle, is that atmosphere in chemical disequilibrium, meaning is there perhaps biotic sources that are replenishing fluxes that's keeping that atmosphere out of equilibrium. So that's a robust detection of biosignatures. And also you can look at surface reflectance features such as, I'll talk about the red edge and the ocean glint. And also you can look at time-dependent modification of the environment caused by biological processes. So this is a fancy way of saying we can perhaps see seasonal variation. So we know on Earth, for example, that vegetation has seasonal variation. Can we detect that and use that as a sign of life on exoplanets? So in terms of, so there's a lot of one major criticism of, I think, the search for exo-Earths and life as we know it is people are like, well, we only have one data point, that's Earth. Well, that's true, and the counter argument is that you have to start somewhere, right? So you have to start somewhere that you know. But in addition to that, I think what's really important to note is that one Earth is really many Earths. And what I mean by this is that the modern Earth as we know it is very different from Earth in the Proterozoic and extremely different from Earth in the Archean. So we can look to the history of Earth to help diversify our pool of data against which we can search and identify biosignatures. So this is a complicated plot, but we'll focus on this left panel here, which is showing, if you tilt your head, billion years ago, so this is like our sun was forming, planets forming, and then we have some record in the rocks. So this is 4 billion years ago in the Archean, and these here, the different colors are different molecules in the atmosphere of Earth as a function of time. So this is modern, this is further back in time. And one thing that you'll notice is that, right, things like oxygen that we take for granted has not always been here at all. So one thing to note is that there's, on the left side here, it's fewer stuff. On the right side here, it's more of the stuff. So oxygen here, we've got a lot of it, it's great. But if we go back to Earth history, the atmosphere was actually anoxic for billions of years. The same thing if you look at methane. Methane was much higher in abundance back then than it is now. And the same with ozone. Ozone really occurs because of the rise of oxygen here. And so again, we can use these 3 different Earths as templates when we look for life elsewhere. So these spectra here are what's called albedo spectra. So albedo is just a fancy way of saying reflection. So these are reflectance spectra. It's the amount of light that's being reflected by our planet as a function of wavelength. So on the modern Earth, right? We've got a lot of oxygen. There's the oxygen buildup leads to ozone formation, and so there's a huge chunk of our reflectance spectra here that's being eaten out, being absorbed by ozone. Water vapor, very good for telling us that there's liquid water. And then back in the Proterozoic, we had our oxygen levels was much lower, and you can kind of see, right, that this whopping signal for ozone, which comes from the buildup of O2, is much less back then. And further, in the Archean, we had no really detectable oxygen in the atmosphere. Instead, we had perhaps a reducing atmosphere with lots of methane, and perhaps a haze. Oh, no. Okay. So, what does this look like? What might this look like to LUVOIR? So here is a reflectance spectrum of an Earth, basically Earth, around a star that's outside 10 parsecs away. And you can see these bars here denote simulated detection with LUVOIR-A. So we can pick up this Rayleigh scattering slope here that's due to that give rise to our blue sky. We can pick up the water vapor bands, and we can pick up oxygen absorption. So with LUVOIR-A, if we were to observe those exo-Earth candidates, remember that the 54 and the 50 and the 30 exo-Earth candidates, if we looked at them for 12 months, we can look at this full spectrum of 24 for LUVOIR-A and 11 for LUVOIR-B of those candidates. So that's pretty good. That means that we're looking for in exo-Earth outside of our solar system, we can try to detect for these water features and methane features. Around 24 and 11 of those in just 1 year. Okay, so with the remaining minute, I'm going to quickly talk about some other ideas about how we can detect perhaps surface features. So this is a really cool idea, I think. As an astronomer, I don't often think about Earth and earthly things, but this is cool because these are observations of Earthshine. So Earthshine is, here's the moon, right? This side of the moon is being illuminated by the sun, so here's the crescent moon. And this side is dark, but the dark side is reflecting Earth photons back at us. The Earth photons are reflected light from our sun. Okay, mind-blowing. Anyway, you take a spectrum here, and that's the reflectance spectrum of Earth, or Earthshine. And here you see that at this time, we were looking at South America, the continent here. South America, the Amazon has a lot of green stuff. So you can see that the spectrum is slightly different from when we're just looking at mostly water. And that's because of this red edge. So the red edge is, or the vegetation red edge occurs because leaves have a certain reflectance spectrum. So chlorophyll, which makes photosynthesis possible, absorbed in the visible. And so we're left with this red edge here when we're looking at the reflectance spectra of the leaf. And this is, to a different scale, what we observe here in the Earthshine spectrum. So this is one possible way of detecting vegetation on exo-Earths. I'm going to skip this because we have no time. And just end here. Thanks. Any questions?
direct imaging?
The question was, I think, when do people decide which mission to go ahead with? And the late 2020. Yeah.
Doesn't it depend on the emission spectrum of the star itself? You have to adjust for the emission spectrum of the star. Like our chlorophyll depends on the emission spectrum of the sun, right? So wouldn't an equivalent star system depend on?
Right. So when we're taking a, that's a good question. So the question was, does it depend on the emission? Reflectance spectra depend on the emission from the star. So yes, when we're directly imaging these exoplanets, right, we're taking a spectrum or an image of the planet, and then we're dividing that by the flux from the star. So we're dividing out whatever contribution the star is making.
Are there any exoplanes that might be first have detectors or like Astronex or the imaging, and have we detected any chemicals in those atmospheres yet?
So the question was, have we detected any exo-Earth yet? Is that the gist of it?
Basically, like, is there an exo-Earth that we're very, like, that one tried these imaging techniques?
Oh.
And so, what chemicals are in that already?
No, we know no exo-Earths. We know of Earth-sized planets in the habitable zones of M-dwarfs, but with our current technologies, we don't know any true exo-Earths. And that is the reason why we want to fly these direct imaging missions, so that we can actually survey different stellar systems close by to us and detect these exo-Earths so that we can look at their spectrum.
Ballpark, in your expert opinion, like 10%, 20% chance, what's the likelihood we'll find aliens?
I'm not the techno-signatures expert. That's, again, Jim Davenport. But I think that the potential for life, as in like microbial life, perhaps, I'm thinking that's what we might detect, rather than like humans. Because bacteria have existed on Earth for many years before we even arrived. They were here in the Archean, the Proterozoic, right? And they were doing anoxic metabolic stuff.
Why does it need to be Earth size? Why is it specifically Earth size or relative Earth size?
Good question. Why are we looking for planets that are Earth size? So that's because I think a couple of reasons. One is that physically, right, we know that there's a difference between gas giants and rocky planets. We can't look for really life on gas giants. And gas giants have larger radii because they have larger masses, right? But specifically, why are we looking for in that like a 20% narrow zone in terms of Earth size? And that's because we don't, if it's too small, then likely it doesn't have, it's also not very massive, and that means that it can lose its atmosphere, like Mars has lost its atmosphere because it's way too small. And also we know from the Kepler mission that about 1.4 Earth radii is this kind of statistical cutoff between planets that tend to be, below that cutoff, planets tend to be more rocky, so they're denser, and then above that cutoff, the planets that we observe tend to be more puffy, so they tend to be more like gas giants or ice giants. Thanks, everyone.